So before we start section 7.1, I'm going to go over this handout on Geometry Review Part 2. This handout is posted as a PDF in Canvas, so if you just want to read it on your own, that's fine. You don't have to watch this video. This should be a review of knowledge from your past. So let's go over these ideas. This is all about circles on this Geometry Review Part 2. So a circle can have a circumference, which is labeled C in this picture. It's the perimeter of a circle. A circle has a center, a point at the very center, and a diameter is a line, straight line from one end to the other of the circle that passes through the center. A radius is kind of like half a diameter. It goes from the center just to the edge of a circle. So for any circle, if we divide its circumference by its diameter, we always get the same number, and that number is traditionally denoted as pi. It's approximately 3.14, but it actually has an infinite non-repeating decimal expansion. You can look up Google things about how many decimal places they've calculated for pi. I think thousands and thousands and thousands. Some people enjoy memorizing decimal places for pi too. I'm not sure why. And so one way to think of what pi means is if you take any circle at all and take its circumference, divide by the diameter, you get pi. Now you can take C over D equals pi, multiply both sides by D, and you end up with C equals pi D, which can be thought of as a formula for the circumference. But since D is equal to 2R, we're going to replace the D with 2R in that formula and write C equals pi times 2R, which is usually written in the order C equals 2 pi R. So that's a formula for the circumference of a circle that we are going to have to use quite a bit in this course. C equals 2 pi R. We're not going to derive the formula for area of a circle. I'm just going to give it to you here. It's a little bit more complicated to derive. The area of a circle is given by pi r squared. And now both the circumference and the area formula have a 2, a pi, and an r in them, but let's just make sure we're clear on the fact that when we say C equals 2 pi r, that's 2 times pi times r. And when we say the area is pi r squared, that's actually pi times r times r. So the area formula doesn't really have a factor of 2. It has 2 factors of r and a pi. The circumference formula only has 1 factor of r, a pi, and a 2. So we'll use both the area and the circumference of a circle in our course. And now we're going to start imagining angles as being drawn with their vertices at the center of a circle. And when an angle is drawn in this way, it's called the central angle of a circle, or acentral angle of a circle. And we'll often use the Greek letter theta. I think I've already introduced that to represent an angle. In this sense, theta is like a variable and can represent any angle measure, or sometimes it's a particular angle measure in a problem. This is very different from the Greek letter pi, which represents a constant, right? Pi is a specific number. We'll use theta to represent just about any old angle that we see. And so here's a picture of a few pictures of some central angles: 90 degrees, 180, 270, 360. And just a couple more facts about circles. Sometimes we're going to talk about a piece of the circumference of a circle, a piece of its perimeter. And that piece is called an arc. A central angle determines an arc of a circle. We would say the central angle cuts out an arc from the circle. Traditionally, the letter S is used to denote the length of an arc of a circle. So if theta is the central angle in degrees, and if S is the length of the arc, then there's a relationship between theta and S given by this proportion. Theta degrees divided by 360 degrees, so that ratio, is always going to be equal to the length of S divided by the circumference of the circle. And I hope you can see why these two fractions would be equal, because theta as a part of full circle 360 is always going to be the same as S being a part of the full circumference of this circle. Those ratios will always come out to be the same. I don't really want to give you a formula for S. I guess you can think of this as a formula, but I just think of it as a proportional kind of relationship that we can make use of in our calculations, and we'll see that in problems. And sometimes we talk about the area of a sector. So S is just the distance along the edge. The area inside is here shaded in this picture. And a central angle also can, is related to the area of the sector it cuts out. And we can also use a proportion, theta degrees divided by full circle, 360 degrees. That ratio always has to equal the area of the sector determined by theta divided by the area of the whole circle. So this proportional relationship we can use to calculate areas of sectors and various other things. So just a couple more facts about circles, a little bit more vocabulary. A line that crosses a circle at 2 points is called a secant line. So here's a secant line to a circle. A line that touches a circle at exactly 1 point is called a tangent line. So there's a tangent line drawn also to that circle. And the word secant and tangent here is related to the secant and tangent functions. It's not at all obvious why that's true. I have a separate handout that talks a little bit about what the connection is between secant lines and the secant function, tangent lines and the tangent function. And there's one very famous fact about tangent lines and the radius of a circle. If you draw a radius from the center of a circle to the point of tangency, that's the point where a tangent line touches a circle, the tangent line and the radius will always meet at a 90-degree angle. They'll always be perpendicular to each other. So that's the end of our geometry review part 2. In our next video, we'll start working on some problems from 7.1.